All right, so we'll do some Administrivia to get started. I want to keep those as simple as possible so that we can get to the good stuff. So there's two pieces of Administrivia you should remember. One is the class website, that's the top line. The second is the class group. Bottom line, you should be registered for the class group. We tried to register most of you. If that worked, you should already have gotten some junk mail from us. So if you haven't gotten junk mail from us, try to go ahead and try and sign up for the group. It's important because you'll get announcements, things like, extensions of homework dates, class cancellations, right? So make sure that you sign up for that. The class website has all of the usual boring class policies on it. It also has things like the office hours, the textbooks, all of that sort of good stuff. All right. So there are a few things I'd like to highlight. The information's on the website, but I figure it's worth anything that's worth knowing is worth repeating. So we'll start with prerequisites for the class. So there aren't any formal prerequisites for the class. However, there are a bunch of things that we're going to pretend that you know. And if that's not true, then that's fine. You can probably pick up a lot of them along the way. But you're going to be sad if you don't know any of these things, right? So the first one is algorithms. So things like basic data structures, complexity theory, like, if I say big O of n cubed, you should know what that means. Programming, we're going to assume that you can program. We're going to assign you programming on the homework assignments. The program's going to be, so the official languages of the course are MATLAB and R. So those are both big, complicated software systems. They're going to be basically, unless there's a reason to do otherwise, we're going to ask you to do your programming assignments in one of those two. There might be some programming assignments where you need to do one or the other because of a specific library that we'll provide. Linear algebra, you should just be comfortable working with matrices. We'll give some introduction to that throughout the course, but again, you should be happy, moving matrices around. Machine learning and statistics, they're going to be the main source of motivating examples for this course. So if you don't care about solving optimization problems related to machine learning and statistics, then you're not going to be very motivated. But perhaps you can deal with that. The most important prerequisite is formal thinking. We're going to do analysis of algorithms. That means we're going to work through proofs, we're going to implement code, we're going to run examples. So you need to be able to just be comfortable going through derivations and proofs. The main work for the course, there are going to be 5 homeworks. Everybody's going to be required to scribe 1 lecture, so you've probably already got an email about that. There's going to be an in-class midterm. It's probably more of a 2/3 term, but we call it a midterm. And then there's a final project. The final project is basically just use optimization to do something cool, right? So that's very, very simple and succinct explanation of what you're supposed to do. Everybody should get together into groups of 2 to 3. Because of the size of the class, we're going to ask that you don't do singletons because it will take forever at the poster session if we have to go through 110 different posters. In the project, we're going to ask you to do a project proposal, a milestone where you tell us what you've done sort of halfway through the project. There'll be a final poster session, and then a final paper describing the project. Final poster session, we haven't completely nailed down the date, but it's going to be December 11th or 12th in the Newell Simon Hall atrium. It'll be about 3 hours long, and it'll start at about 3. That's a reading day, by the way. The Wednesday is a reading day, so that should minimize final exam conflicts if we manage to do it on that day. Okay, scribing basically means writing up like a LaTeX file of the contents of a particular lecture. There's going to be 2 to 4 scribes for every lecture. Everybody should only have to scribe once per term. The scribes coordinate to make one really good write-up. The TAs then take a look at the write-up, and then the professors take a look at the write-up, and hopefully at the end it's a very nice, accurate write-up that everybody can use to study from. This is new this year. We haven't done scribing in this course before, so if you have suggestions that for how to improve it, we'd be happy to hear those, or suggestions about basically what features of a scribed lecture make it most useful to you. The idea is to make it so that you guys have an easier time studying, and so if we're not succeeding in that, we want to know about it. Late days. We're going to give you 5 late days. So you can use 2 on one homework, 3 on another homework, all 5 on one. This is not just a present that we're giving you, right? This is intended to make it so that we don't have to specially handle every time somebody has an illness or travel or a holiday that they have to attend. It's basically your responsibility to allocate them wisely. So, for example, if you use all 5 late days at the beginning of the semester to go to parties, and then you get sick at the end of the semester, we're not going to be so sympathetic. Some deadlines are going to be non-extendable. You can always hand things in early. Right, funny joke. And we'll let you know what those are. Working together. So everybody has to hand in their own write-up, but we encourage study groups. It makes it a lot easier to learn some material, to go over it with friends. The basic principle, there are 2 of them. One of them is you should always write up your own solution with closed notes. In other words, don't look at any notes that you made from the study group while you're writing up your solutions. That's what that means is that you have to have the material in your head at least long enough from when you closed the notes to when you write it up, right? And that actually, it's a very small thing, but it makes learning work a lot better. Second thing is, if you have any significant collaborations, just disclose them on the front page of the homework so that we know about them. We have some great course faculty. So I'm Jeff Gordon. The other professor is Ryan Tibshirani, who is in the back. Do you want to stand up? All right. We're going to be doing tag team lecturing. So if you ask us too many difficult questions, we'll tag out and let the other ones start answering them. We have 4 TAs. Could the TAs stand up? So we have Shiva Kaul. There's Kevin Wah in the back. And then I think the other 2 TAs are currently still on their summer internships, so they'll be back in a week or 2. Everybody has office hours. They're listed on the website. We tried to spread them out so that there's always somebody for you to talk to within a day. There's going to be recitations. There are no recitations this week because we don't have anything to recitate about yet. But it's going to be... we set it up so that there are 2 recitations in a week that have the same material. They're at 2 different times, so hopefully you can make one of them. And also because the course is big, right? We want to sort of try and distribute people between the 2 recitations so that they don't get unmanageable. Auditing, we welcome auditors. We ask that you please sign up for auditing. My, that's a loud fan. Hopefully, you guys can all hear me over the fan, I hope? Okay, good. We ask that you sign up for an audit. That means you register for the course and then have me or Ryan sign a form. Rather than just sitting in, the department gets us in trouble if people do that. We don't expect to deny any audit requests. The wait list should be empty. If you're still on the wait list, come see us and we'll try and make sure that that's not true anymore. And then again, new this semester, we're going to try videotaping the courses. So you can see the nice video setup in the back there. That's the same camera I used to videotape my 3-year-old daughter dancing in her fairy costume. So you guys get to decide whether the lectures are more or less interesting than that. But because this is sort of the jury-rigged solution, it might not work, so don't depend on it. Try to attend class if at all possible, because something might go wrong and we might not be able to videotape a particular lecture. Second, it's just a lot more fun to be in class, right? Like, it's the difference between a live performance and listening to a recording of your favorite band. Again, you can decide whether I'm as interesting as that. Right, and so we'll try and post it. Let us know. Also, we're going to be experimenting with a particular hardware and software combination, so if there are any features of the videos that make them easier or harder to use, please let us know. All right. Most important, work hard, have fun. So any questions about the policies? Yeah. Yeah, the two recitations are supposed to be the same material. They might be slightly different because people ask different questions, but the goal is to have them cover the same material. Yeah. Yes, the scribe template is up. It's off of the lecture page on the course website. Yeah.
For homeworks, do we have to make them into an X form, or do you accept write-ups for homeworks?
You should be able to handwrite the homework as long as your handwriting is legible enough for the TAs to read it. Basically we'll instruct the TAs not to give the benefit of the doubt if they can't understand the handwriting. We'll give you instructions for how to hand in the homeworks when we hand out the first homework. Any more questions? All right, let's get started with the fun stuff. So looks like we spent 10 minutes on the Administrivia. Somebody once told me that the less time a course spends on the Administrivia, the harder and more interesting it is. So we'll see if that's true in this case. All right, so let's start with an example of an optimization. This is the sort of thing that all of you guys will be able to analyze in your sleep by the end of the course. So suppose we have a simple economy that has M agents in it and N goods, right? These goods are things like, a left sneaker and a right sneaker, or tickets to a Pirates game or something like that, right? So each agent has the possibility of producing or consuming all of these goods. For producing, they have a cost of production, which is, so we have a vector P for each agent. So we'll call that PI, and each component of PI is how much agent I produces of of one of the goods. So component J of PI is how much agent I produces of good J, and we'll say that the cost of producing for agent I is SI of PI, right? And the utility of consuming is going to be DI of CI, right? So we'll have a vector both of production and of consumption. They're both length N because they're N goods. S stands for supply, D for demand. That's the mnemonic. And the idea is that the supply function, it's going to get harder and harder to produce more as you get higher and higher production. So it's going to have increasing slope, whereas there's going to be sort of a satiation effect for demand, so the slope's going to get lower and lower as you demand more and more, right? So an extra Happy Meal is worth less if you already have 100 of them than it is if you have 0 of them, right? All right, so then our goal is going to be, let me get my, whoa. Do we have the, is that back yet? All right. There we go. All right. I'll have to remember not to sleep my screen for the rest of the lectures. All right. So what we want to do to get the best possible strategies for all of the agents is to take the maximum, right, over all possible PI and CI of the sum over all agents I, right, of the cost, well, so the utility they get, DI of CI, minus their cost of production, right, which is SI of PI, right? And so this is that's the objective function of our optimization, right? Maximize the happiness, the sum of happiness over all agents. It's a very democratic objective. We don't favor one agent over another. And then there's going to be a constraint which says that the sum over I of consumption has to equal the sum over I of production, right? So goods don't get created or destroyed during the optimization. All right? Yeah.
You're drawing a multi-dimensional picture, but since there's no, right, since you are separating all the components in SI, VI, these goods are not like complementary.
So SI is a function of the entire vector.
Okay, but
So it could,
PI.
right?
PI
is in Rn. It's a vector of all of the productions for the ith
So
agent.
this supports complementary.
It supports exactly complementary or substitutable goods. So just to clarify that question, complementarity between goods is like a left sneaker and a right sneaker. It means that your value for the two of them together is more than the sum of your value for each of them alone. Substitutability is something like, let's say, tickets for a opera and tickets for a Pirates game at the same time, right? I can't use both of them, and so I get less than the sum of their utilities.
I guess what I should have asked was that the difference in DIC and DICI, you're not getting across individuals. There's no notion of individual one, like it's not going to feel better in individual. There's no joint. See what I'm saying? Right.
There's nothing across individuals. I don't have envy for seeing somebody else get more tickets to Pirates games than I do. I don't have. I don't feel good for them. It's only within a single individual. All right. So does everybody understand what this optimization problem looks like? Sort of makes sense that this is a reasonable way to set up the problem. All right. So. That thing on the bottom left magically becomes LaTeX at the top of the slide, okay? So I don't have to write it again. So now how are we going to solve this optimization problem? Well, there's this thing called a Walrasian equilibrium, which I'm going to describe right now. And the way it works is that so before we have no idea of money, but imagine we introduce money into the system, and we put a price of lambda j on good j, right? So that means that I say tickets to the Pirates game cost $5, tickets to the Steelers game cost $500, right? Whatever the appropriate prices are. And then suppose that I let the agents optimize their production and consumption each independently, right? So what does that look like? So what we're going to do is, for agent I, we're going to have di of ci minus lambda dot ci, right? So this is the benefit I get from consuming minus the total cost that I pay for everything, right? So the j component of this is the price for good j. The j component of this is how much I consume, and so the dot product is the sum of the product of the price with the consumption. And so this is how much I get from my consumption, right? And then for production, I'm going to have pi of si, again, minus lambda dot si, right? And I'm going to have the difference of that for each agent, right? And the interesting thing now is that there's no cross terms. Each of these is within a single agent. And I'm going to now drop the constraint that supply has to equal demand, that production has to equal consumption. And so that means that if I optimize each of these independently, that's the same as optimizing the sum over all agents. Okay? And then this is going to be, again, a max over Si and Ci. Okay? And now I've dropped the resource constraint. All right, so I had to guess what is the value of this particular lambda. What are the prices? Suppose that I happen to guess a lambda such that production equals consumption, right? So why might something like that exist? Well, if I set a high price, the agents are going to produce more because it benefits them to sell what they've produced. And they're going to consume less because they have to buy what they consume. If I set a low price, the opposite's going to happen. And so somewhere in the middle, there's like the Goldilocks price. Yeah. Oh, did I get the SIP? I got SIPI. Sorry. This should be SI of PI minus lambda dot PI. All right. Thank you. So I guarantee there's going to be at least one mistake in each lecture to keep you guys on your toes. So you guys have to catch it for me, right? So that I don't have confusing slides posted on the web forever. I'm sorry? Yeah. Oh, yeah. Good point. This is PI instead of SI. Thank you. All right. So you could imagine that if I set the prices right, then it might just happen that supply and demand are matched, that production and consumption are matched. And supposing that I could find that, right, that magic vector of lambdas, that's called a Walrasian equilibrium, after this guy, French economist from a couple of centuries ago with the unfortunate name of Leon Walras. Not related to, you know, Auguste Dolphin or something. So if such a thing exists, it's called a Walrasian equilibrium, meaning the combination of that vector of prices lambda and all of the SIs and PIs that are optimized for each of the agents independently. And suppose that happens, well, the lambda.ci is going to cancel with the lambda.pi, right? And so I will have maximized the sum of DICI minus SIPI, which was my original goal. Okay? So, small remaining problem, how do we figure out lambda, right? Or even does lambda exist? So it turns out that this guy, Walras, also proposed an algorithm, which is called tátonnement, which is French for searching. Sounds better in French. And the algorithm is actually quite simple. You start off with some fixed vector of prices, let's say all zeros, and you just repeat forever, or until you get tired. Every agent solves for the vector of prices solves for their vector of production and consumption at the current prices. And then if you define, let's see, if you define C to be the sum over I of CI, right, and P to be the sum over I of PI, right, total production and total consumption, and you take some learning rate, right, so this is greater than 0 and sort of small. What you do is you just add the difference between consumption and production to your prices. So what's that going to do? That's going to make it so that if consumption is higher than production, right, the prices are going to increase. That seems reasonable. If it's the other way around, if production is higher than consumption, the prices are going to decrease. And so that should hopefully help to correct the imbalance. And so hopefully after a whole bunch of iterations of this, we converge and get to a Walrasian equilibrium. Okay? So it's a fairly simple algorithm. And so far we haven't argued at all that it works. But it happens to work in a lot of cases, which is why this guy got his name on it. So does the algorithm and the optimization problem make sense? All right, I see a bunch of nods. That's good. I'm sorry, could you say that louder? Yes. Right, lambda will be unchanged once you satisfy the constraint. Right, so you start off, if everybody optimizes independently, you'll start off with the sum of CI not equal to the sum of PI, meaning you don't have a valid solution yet. And then that will change the prices. And eventually, hopefully, you'll achieve that C is equal to P, at which point the vector of prices will stop changing. Right, so it depends what the supply and demand functions look like. You could put bounds on how much they can produce or consume, and just say that they produce or consume a finite but arbitrarily large amount. The question was, won't some of the productions and consumptions become infinite? Right, so you'll start off, if you have zero price, everybody's going to say, well, I won't produce anything, zero production, but I'll consume as much as I possibly can. But let's say that you have a finite appetite for Happy Meals or whatever the commodity is, and so you can't possibly consume more than 1 million. Yes? I'm sorry? Yes, C and P are both vectors. They are the same size because they have one component for each good, right? So there's one CI and one PI per agent, and all of them have length equal to the number of goods. Yes? That's okay. Yeah. So you've actually hit on an important variation of this problem. If you have what's called free disposal, then meaning that if you have extra of some good, you can just throw it away at no cost, then the prices can never go below zero, and you can impose that constraint if you want to. But right now, we're assuming that it's possible to have too much of something, right? That if you have 1 million Happy Meals, they'll fill up the lecture hall, and we'll have to figure out some way to cart them off, and it'll cost us something. I saw a hand over here. Yeah. So the question was, shouldn't the prices be constrained always to be positive? And the answer is, that's a different version of the question of the problem where you have free disposal. All right. Cool. So here's what happens if you actually run it. So I generated a random market with basically a few agents, like 3, I think, and random supply and demand functions that looked like the plots that I showed you. And I ran the algorithm. And so if you look at the right-hand plot, that has the prices, which start off at 0 below the bottom left corner of the plot, and they very quickly sort of converge to a limiting value. You can see that they don't take a straight line path to get there. They could take a pretty wiggly path. They happen to only have a few wiggles this time. And then on the left-hand plot, you see the total production and total consumption across all agents. So as somebody already pointed out, the total production starts at 0. The total consumption starts off really large, but as the prices converge to their optimal values, the circles and the x's converge to one another, and we are happy in the end. Okay. So, cool, it actually works. I picked this as an example to start off the course because I think tátonnement is a pretty cool algorithm. Why do I think so? Well, the algorithm is nearly obvious once you figure out the way that you're going to set up the problem, right? It seems like each step sort of really makes sense why you would do it this way. But it took until 1874 for somebody to figure out how to set up the problem this way, right? Euclid could have figured it out in principle, but he didn't. The other thing that's kind of interesting is that the analysis of the algorithm is subtle. So Walrus didn't know that the algorithm converged for sure. It turns out that it does under certain circumstances. But in order to prove that, you're going to need some of the things that we're going to teach you later in the course. So hopefully that's motivating for you to actually stay with the course and learn those things. For example, the idea of duality in optimization problems, dual decomposition, which is a way of making sure that you can break up a big problem into a bunch of smaller pieces, and convergence rates of gradient descent in different circumstances. And there are variants of the problem that need even more subtlety. So for example, if you have indivisible goods, right? So, you know, if you're working with something like water or steel where you can divide it arbitrarily finely to within the precision we can measure it, that's one thing. But if you're working with, let's say, factory buildings, right, where you're going to buy, let's say, 0 to a dozen of them, and the distinction is really big between buying 3 and 4 of them, right? That makes the problem much harder. So, that's the example. It's an instance of what I'll call our typical optimization problem. So our typical optimization problem is going to be, it's going to look something like this. We're going to minimize some function f of x, which is called the objective, subject to some constraints. So the constraints are going to be gi of x is less than or equal to 0 for some set of functions gi indexed by a set which I'll call the inequality constraints. And hi of x is equal to 0 for I in some index set which I'll call the equality constraints. Right? And sometimes we have additional restrictions on x, like x has to be an element of some discrete set, but we'll ignore that for the purposes of at least the first big part of the course, right? So in the previous example, right, we had, in the tátonnement example, we had f of x equal to the total utility across all agents, both from production and consumption, and we had one equality constraint that was linear. Total production had to equal total consumption. Someone else suggested a linear inequality constraint, right, that production or consumption had to be positive or that prices had to be positive. And different variations of this problem will have different names and different properties, right? So there's not actually any need to separate it out this way. For example, I could take any constraint and add it to the objective by having a function, by having a sum, a term in the sum and the objective that says if the constraint is violated, then you pay a lot, maybe even an infinite amount, right? Or I could take two inequality constraints and use them to simulate an equality, right? So, you know, ax equals b is the same as ax is bigger than or equal to b and ax is smaller than or equal to b, right? But it's going to help for the analysis, for the development of our algorithms to be able to split things apart like this, right? So this is going to be sort of our typical problem setup that we're going to be analyzing for the first big part of the course. And the different properties of these different functions turn into different optimization problems that have different names, different algorithms, and different sort of difficulty levels. So for example, if f and g are all linear, right, we get the famous linear program, or LP. If f and g are all convex, we get the convex program. So convex programs are nice in the sense that they are not really that much harder than linear programs, but a lot more expressive in some ways. And so a lot of papers these days are, we take this problem that we care about, we reduce it to a convex program, we apply the techniques from this course, we're done, right? We have a plot at the end of the paper that shows that the algorithm works. Okay. Did I see a hand over here? No, okay, my peripheral vision is tricking me. So there are lots of things in between linear and convex programs, and of course there are things that are not convex programs. So in general, if something is not a convex program, then it's hard to solve. But whether it's a convex program or not can depend on how you set up the problem, right? That's the nice thing about your problem. You get to decide how to set it up. So an example of something that's between linear programs and convex programs is a semi-definite program. So I'll just write SDP here for semi-definite program. So if the objective function is linear and we have one inequality constraint that is basically on the smallest eigenvalue of a matrix variable, right? So what I've done is I've taken our vector of variables x, and that MATLAB stuff reshapes it into a matrix by taking, the first set of variables, making them the first column, the second group of variables, making the second column, and so forth. And then the smallest eigenvalue tells us if the smallest eigenvalue is positive, then it winds up being a positive definite matrix or non-negative positive semi-definite matrix, right? And we also wind up needing an equality constraint that, so we'll call this thing, we'll call that capital X. I'll do that to make sure that you can tell it from a little case x. So for a semi-definite program, we need capital X is equal to capital X transpose, right? It's a symmetric matrix. And then we're allowed to have any number of linear constraints. So any linear HI. Okay. So any questions about the typical optimization problem, what it means or what the distinctions are like? Yeah. Right. So these guys actually got the word program before we did. The question is, why are they called programs? So a linear program, you can think of it as like a program for running your business, right? Like a policy program, right? So these guys got the word program before we computer scientists got it, and so it's a historical usage. And of course, in this course, you're going to be writing the computer science kind of programs to solve these kind of programs. So, all right. So this typical form, it's everywhere. I'm sure that I have personally seen at least 1,000 papers that use that particular form of a program. And it's a really interesting problem. So linear programs in particular are at least as old as Fourier. So that's pretty old from the point of view of computer science. The first practical algorithm for them didn't happen until 1947. That was George Dantzig, the simplex algorithm. And for a long time, the best runtime bounds for simplex were exponential, but yet the practical performance of simplex was observed to be pretty good, right? So this was a source of consternation for complexity theorists for a long time, and still is for certain questions. So because of this worst case exponential bound, when people started looking at the P versus NP question, a lot of people thought linear programs were going to be NP hard. It turns out they're not. So in 1979, a guy named Kacchian came up with the ellipsoid algorithm, which was the first polytime algorithm for solving linear programs. And then a few years later, Karmarkar came up with the affine scaling algorithm, which is widely thought of as the first practical algorithm that's in polytime for solving linear programs. And in fact, even the simplex algorithm has been proven to work in polytime for most linear programs in a pretty strong sense. And that's a quite recent result. And it was a big deal when it came out. The other thing that's interesting is that linear programs are P-complete. That means informally that they're at least as hard as any other polytime solvable problem. Formally, it means that there's a log space reduction from any other polytime problem to linear programming. Yeah, so I think they're a pretty cool problem. Hopefully you will too after seeing all of the nice stuff that we do in this course. They're not just ubiquitous sort of in the world in general. They're ubiquitous in machine learning and statistics. So It's not a bad characterization to say that all of machine learning and statistics is phrased as you set up an optimization problem based on a statistical model and then solve that optimization problem. That's a little bit of an overstatement, so we'll go into some exceptions. But for example, so let's take audience suggestions. What's a statistical problem that involves an optimization? What's that? So regression, that would have been one of my first ones as well. Any other ones? PCA, yeah, that's right. So you can phrase PCA as an optimization. So PCA is principal components analysis. I heard maximum likelihood from somewhere in back. That's a generalization of the regression suggestion. So that's a good one. Okay, more? Support vector machines, yep. That's a good one. So I'll just write SVM because it takes me a long time to handwrite support vector machines. Yeah. So there's a few more actually that are maybe more general even than that. So suppose that you wanted to do planning. Right? So you can think of that as at least partially a statistical problem because there might be uncertainty in the world. So if you wanted to solve, for example, a Markov decision problem or even a partially observable Markov decision problem, right? Those would be optimizations. You can phrase those as optimizations. Maximum entropy, resource allocation, right? So like that, the Walrasian equilibrium problem. Again, trying to fit the behavior of that to an actual observed market would be a nice statistical problem. How about exceptions? Can people think of some stats problems that are not phrased as optimizations? This one's kind of tricky because sometimes there's a way to take something that's not obviously an optimization and make it into one. Yeah. Mm-hmm. So we want, like, for example, integration over a posterior, right? Although, in some sense, optimization is a subproblem of that one because typically what will happen is in any interesting problem, there'll be some huge space of possible parameter values and the posterior will be peaked in a very small set and you want an optimization to try and find where that peak is, right? And in order to be able to integrate, you have to know where the peak is, otherwise you're going to miss a lot of the mass in the integral. Other suggestions? Statistical testing. That's an interesting one. I don't know whether that involves an optimization or not. Like in some, like for example, for a lot of statistical tests, the recipe is first find the maximum likelihood estimator and then do something with it, right? So I'll put that. I'll put hypothesis testing with a question mark here, right? Because yeah, it might involve it as a subproblem, right? But it might involve optimization as a subproblem. But yeah, there's more to it than just the optimization. Any other? Yeah. K-nearest neighbors. So more generally, non-parametric estimation, right? So that's another good one. Because, and again, it's in some senses a questionable case because there are optimization-based non-parametric questions, although K-nearest neighbor is a good example of something that's phrased as an algorithm rather than as an optimization. So this is interesting. You're getting a whole bunch of ones that I wasn't thinking of. The next one I was thinking of was belief propagation, right? So that is, whoops. So that's an interesting one where, given a graphical model, you want to find, let's say, a distribution, a conditional distribution over some nodes, given values for the other ones. It's not obviously formulated as an optimization problem. People have made various approximations to it that are optimization problems, but natively it doesn't seem to be one, at least not in a way that I can figure out. Another one I was thinking of was there are some game theory questions that you can think of as being about uncertainty that are also not obvious how you phrase them as optimization problems, although there are also some game theory questions that do look like optimization problems. So again, I'll put a question mark by that. Property testing? Is that different from hypothesis testing? Like linear, sublinear time algorithms. Okay. Okay. I guess I don't know enough about that to answer whether it is or not, but I'll trust you and I'll put it under the exceptions. I'm sorry, what was that? You're not sure. Okay, well, I'll put a question mark by it then. Well, but typically those are optimizations, right? You're trying to find something that optimizes the fitness.
But the constraints are not linear or convex.
Right, so it's not a convex optimization, but it is an optimization, right? So yeah, a lot of the interesting optimizations are really difficult to phrase as convex ones, but I'm still going to count those as, you know, we cover all optimizations in this course. We aren't going to limit ourselves to just convex ones. Hopefully we'll have time at the end to talk about some techniques for making non-convex optimizations easier. All right. So why is it that this happened, right? Why is it that so much of machine learning and statistics is phrased as optimization problems? Well, there are a lot of advantages to doing it this way. One, I'd say maybe the biggest one, well, who knows if it's the biggest. One good one is that once you've set it up as an optimization problem, there are sort of fast generic algorithms that you can use to solve it, right? And that's one of the things you're going to learn in this course about what are all of these fast generic algorithms. So there's sort of, once you've done this, done the work to set your problem up as an optimization, there's a big set of hammers you can hit it with. Another one, of course, is that optimization problems are pretty expressive, which sort of goes with the fast generic algorithms, right? You often can set things up as an optimization, and then once you've done it, it often leads to a good algorithm. There's also, from machine learning and stats point of view, often once you've set something up as an optimization problem, there's a nice way to connect the optimization objective to statistical performance of the solution that you get in the end. And so that licenses approximation algorithms as well as exact algorithms, right? So I'll just write that as connect the objective to the statistics of the problem. And then finally, there's often a bunch of standard transformations of the problem, right? So once you've set the problem up as an optimization, there are standard transformations that you can use to turn it into a different optimization that might give you more insight into the problem, might look really different after some of these standard transformations, give you a lot of insight into the problem or suggest different algorithms that you can use to solve them. And I'm thinking about things like duality or relaxation of the problem among these transformations. Yeah? Right. Well, so the usual response is, well, do it differently then. But sometimes you're stuck, in which case you wind up needing to use a very, what do you call it? A very generic optimization algorithm, in which case you won't necessarily get good performance. performance. So something like a genetic algorithm, a genetic search, is something like it's rarely the best answer to any problem, but it can answer a lot of problems, right? All right. So there's a lot of advantages to doing it this way, and there's which is why a lot of people do it this way. There are a few disadvantages. So, the first disadvantage is that you have to take this course first in order to understand how to do it. But more seriously, we'll give you a sort of standard toolbox of ways for doing this, and they might wind up losing something in the transformation, right? So you have some idea in your head of what the problem is, and then you do a transformation to an optimization problem, and it might wind up that you lose a lot of the intuition that you get, or you lose some property of the problem that makes it easy to solve. And so, as with any sort of toolbox, you have to watch out for that. But there are sort of particular things to watch out for that will hopefully alert you to throughout the course. All right, so one of the other things that we're going to try and do is give you a break partway through each one of our lectures. So I was thinking that now might be a decent time for a break. Just be a few minutes, and then we'll get up, do jumping jacks, whatever, and hopefully people will yawn less once they're sitting back in their seats. So back in a few minutes. All right, so everybody, let's get sat back down again, please. And so there's another 20 minutes left in the lecture. So we'll go through some more of the slides. I won't be able to finish all of the slides I've prepared, but that's never a problem. I can always do them later. What I want to do now is sort of give you a more detailed preview of what the main idea of the course is. Right. So what we're trying to do is give you the skills to be able to take an informal problem that's specified in your head only, maybe natural language, maybe it's somebody else's head instead of yours, and turn it into a formal optimization problem that you can then choose an algorithm for and solve, right? And it turns out that there's a lot of choices, right, when you go through this process. The most difficult choices are actually at the front end, when you go from the informal specification of the problem to the formal one that you could put down in the computer. And they're also the most difficult to teach, but one of the goals of the course is going to be to give you examples of how that happens, so that then you can do it yourself for whatever problem you come across later. Once you've written it down, then there's a bunch of tools in the toolkit. You can do sort of standard transformations on top of the problem to bring it to a form that's easier to solve. These include things that I mentioned before, like duality and relaxations and other approximations. And then finally, once you've transformed it into the end form that you're going to solve, you have to select an algorithm that's appropriate for solving it. And so there's a lot of choices for algorithms. Some of the ones that we're going to talk about later in the course are first-order algorithms versus interior point algorithms versus the ellipsoid algorithm versus cutting plane algorithms. The properties of the functions f and g and h in your setup of the problem turn out to have a big effect on how easy or hard it is to solve. So, for example, things like smooth versus non-smooth functions, or sometimes there are ways you can split into a non-smooth but still easy to handle part and the smooth part. There are sometimes you can use eigensolvers to solve optimization problems. That's another different class of algorithms. Sometimes you can use message passing, or in different fields they're called relaxation algorithms to solve the problems. And all of these algorithms have sort of different requirements from the problem for what's going to make them work well versus totally fail. And those requirements wind up getting propagated backward through all the other steps in the problem, right? So once you try and select an algorithm, but maybe you can't find a good algorithm because of some property of the problem, well, then you go back and you figure out, well, maybe I could set it up in this other way and that will get rid of that property. Oh, but it introduces this other property, but maybe I can use some kind of transformation to get rid of that, right? So it's sort of a process where you go through backward and forward this whole chain, and that's what we want to give you experience with in this course. So I want to, that's sort of very abstract. I wanted to go through some examples of interesting optimization problems, and maybe if we have time, a whole worked example of how to go through this process. So I mentioned some of the consequences. Here's just a survey of a few of them. So if you choose a first-order algorithm, by which I mean something like gradient descent, versus a higher-order algorithm, like, for example, Karmarkar's affine scaling algorithm, you get a big difference in the performance characteristic. So the two big differences are the number of iterations. So the higher-order algorithms are going to typically require many, many fewer iterations to reach the same level of accuracy. Typically, the first-order algorithm will be a number of iterations polynomial in 1 over epsilon, where epsilon is an accuracy requirement parameter. And for a higher order algorithm, it'll be polynomial in the log of 1 over epsilon, right? So we could be talking, thousands or millions of iterations versus 10, right? So that's a big difference. On the other hand, the cost of each iteration could be very wildly different as well. So in first order methods, the iterations are typically very, very cheap. They don't do as much, but they're cheap. Versus an interior point type algorithm, a higher order algorithm, you'll typically have an n cubed per iteration, where n is the number of variables or the number of constraints. Right? And so it's sort of a trade-off between whether you want really, really high accuracy or whether you want the ability to have many, many variables and constraints. If you have your problem balanced, number of constraints about equal to the number of variables versus not, that can affect your algorithm choice. So for example, the ellipsoid algorithm turns out that it can handle problems with infinitely many constraints as long as the number of variables is finite, right? And that's kind of cool, right? All you need is what's called a separation oracle, means that you can go and find a violated constraint if there is one for a particular solution. And so you can have infinitely many as long as you can find a violated one. And so, if you're stuck with infinitely many constraints, then you might be restricted in the number of algorithms you can apply. You might have properties of either the solution or the problem. So things like sparsity or locality or other special structure. These could be in the solution, so meaning that there are only, for example, a few non-zero variables out of a very large number of variables. Or they could be in the matrices describing the constraints. So you could have AX equal B, where A is a matrix with only a few non-zero entries, and that could affect the algorithms that you can apply. So for example, if I can compute A times X quickly, even if A doesn't have any other special structure. Right? I can do that, for example, if A is sparse, but I might just have somebody hands me a piece of C++ code for computing A times X. That might actually be enough to enable me to apply certain algorithms. Versus if I have actual access to the entries of A, that would enable a different set of algorithms. Simplex versus log barrier, right? So even though there's in many situations a worst case complexity bound for simplex compared to log barrier, sometimes in practice simplex is going to wind up being way faster. So for example, my understanding is that for certain network flow problems, simplex is still the way to go, even though maybe in theory log barrier has a better asymptotic performance. Or at least better bounds that we can prove now. Who knows what the actual asymptotic performance is. Your functions f, g, and h, are they differentiable? Are they many times differentiable? Are they strongly convex? Self-concordant? We'll define all of these terms later in the course. Submodular, right? That's another nice property. I mentioned splitting methods for splitting f into g plus h. So f is your objective, and let's say you can split it into a part that's nice for one reason and another part that's nice for another reason. That's often a helpful thing to be able to do. Maybe f isn't nice itself, but maybe it's close to a nice function in some way. That can be important. And also, it turns out that there's a lot of interesting theorems you can prove using optimization techniques. And the optimization techniques that you want to use in the theorems are maybe different than the ones you want to use in the actual implementation. All right. There are tons of examples of optimization problems. I'm not going to go through this entire list because it would take me, well, the rest of the course. But maybe if anybody has, there's probably something interesting to say about each of them. So, we'll take audience suggestions for ones of these I should say a sentence or two about. Sensor placement, right? So that's a nice one. So the problem with sensor placement is you have maybe a 2D area that you want to cover with physical sensors, and you want to get as much information as possible about some quantity of interest. And so there's been a bunch of recent work that I think is pretty interesting, where the total amount of information that you get is a function that has this property that I mentioned called submodularity, which means it's sort of a diminishing returns property, that if you already have a lot of sensors out and you add a new sensor, you'll get less information than if you have only a few sensors already out there. And that turns out to enable a nice set of approximation algorithms. So you can run, for example, a greedy algorithm where you always put the next sensor in the place that increases the objective the most. Turns out to have good bounds. You always get within like 2/3 of optimal if you do it that way. Other ones? Parsing, yeah. So the idea here is that you have a string of words in, let's say, a natural language, and you have a grammar for that natural language, maybe annotated with probabilities for each action in that grammar. And it's an optimization problem to find the most likely parse for a given string. And there are very interesting dynamic programming algorithms. Two of them are the early parser and the inside-outside algorithm. And these dynamic programming algorithms wind up giving you much, much better performance than the sort of naive search algorithm that you would do if you didn't sort of really understand the structure of the problem. Experimental design. In many ways, that's actually kind of similar to sensor placement, right? So here it's sort of a space of experiments, right, that you're thinking of doing, and you want to get the most information possible about some quantity. And you have to decide, based on everything that you've done so far, what's the best experiment to do next. I actually have, I think, an example of that in another couple of slides, so you'll get a little bit more detail about that one. Yeah? Compressed sensing, right. So is your example that you're thinking of giving, is that a compressed sensing example, or is it more lasso? Okay, so compressed sensing is, it's the following problem. You have some complicated high-dimensional thing that you want to sense, and you have a sensor that you want to design a sensor to be able to sense this complicated high-dimensional thing. So maybe it's an image of some slice of somebody's brain in a CAT scan, right? And it's difficult to acquire images directly of the inside of somebody's head, and so you're restricted in the sort of physical sensor design. But you can often design things so in a particular way that the measurements you acquire, you can acquire only a fairly small number of measurements and yet still be able to accurately reconstruct the image that you're looking for. And the property that you're trying to exploit here, there's sort of two properties. One is that there's some basis which makes the image sparse, right? So I mentioned sparsity as one of the properties that makes a difference for optimization. So for example, images are often sparse once you transform them into a wavelet basis, right? Or approximately sparse. So that's one, and the other is that you have to design your measurements in a particular way, essentially so that no two measurements are very highly correlated with one another if you select a random image that you're trying to measure. And once you do that, then you can design an optimization algorithm that's able to, with high probability, reconstruct the image you're looking for accurately. All right. So let's do, I think we might have time for one more example. I like this one. You can actually play with this on my webpage. So let's see, I think I have it set up here so that I don't have to load it. All right, so This is one-card poker, right? Can't play it in Vegas, but it's a nice, simple game. So we deal. We've won nothing so far. That's better than what's going to happen in a little while. Computer and I each ante $1. I get delta 3. Any thoughts about whether I should bet or pass? Pass, all right. So pass means $0 bet. The computer raises the bet to $1. Ah, darn that computer. What do we do now? Do we call or fold? I hear fold, all right. That's betting 0. You fold, you lose. Your total losses are now $1. We'll play another hand. All right, we've lost $1 so far. I have a jack. Any thoughts about whether to bet or to pass? Bet. All right, we're going to bet $1. The computer folds. Ooh, we win $1. All right. Okay, so you can see what this game is like, and you can play it for an arbitrary amount of time on my webpage. I don't necessarily recommend the arbitrary being that big, but it's kind of addictive, as it turns out. And yeah, so the optimization problem here is to find an optimal strategy for playing this, right? And so this is a zero-sum game. If I win, the computer loses, or a constant-sum game, because no, it's zero-sum. If I win, the computer loses, and vice versa. It turns out that there's actually, even for this simple version of poker, a very, very large number of strategies. It turns out that there's 2 to the 26 strategies for the second player, that's the computer, and only a little bit less than that for the first player. Okay? So it actually would, even for this very simple one, if we solved it naively to find a minimax equilibrium, it turns out that there's a linear program for finding minimax equilibria, and the size of the program is the product of the number of strategies for each player, right? And that's, 2 to the 26 squared is a pretty big number. But there's a clever way you can reset up the problem. It's called the sequence form. You can look it up. Online because not really the subject of the course, and it would take a while to explain. Which gets it to a linear program that has on the order of 100 variables, right? So 2 to the 26 times 2 variables down to 100 variables seems like a pretty good improvement. And so I just solved the problem of finding an optimal strategy. You can actually download the code from this web page if you want to take a look at it. Or you can look at the optimal strategies. So we have down here the optimal strategies. So here, this is the betting table for player 1. On the first round is blue. This is the probability of betting given that you're delta 2 through an ace. Right? So you want to bluff, actually, if you're delta 2 or 3. So you guys didn't necessarily pick the right thing when we didn't bet on the 3. We could have made the computer fold. And we want to slow play, right, sometimes when we have a high card. So we don't always want to bet so that the computer doesn't know that we have a high card whenever we bet. And then on the second round, it's actually much more simple. If we have a high card, we always bet. If we have a low card, we don't always bet, and in the middle we have some flexibility. This betting table turns out not to be unique, but this is an optimal betting table. And then for the other player, it turns out I can't scroll sideways. Well, there's a betting table for the other player on the page as well. So yeah, and so through basically cleverness in the way you set up this problem, you go from an optimization with millions or worse variables down to an optimization problem with 100 variables, right? So pretty good time to call it a day for that one. All right, so this is a toy example, obviously, but it turns out that you can use this same method, turn the sequence form into a linear program and solve it. That actually will get you a competition level 2-player limit Texas Hold'em player. That's work done here at CMU by Thomas Sandholm and some of his group. And what you have to do there is you have to abstract the game by clustering together similar hands and similar betting sequences. And you have to buy a really big workstation, right? And those two things will then get you a winning Texas Hold'em player when you do them together. All right, so another interesting example, this one's kind of fun. This is dynamic walking. So let's see if we can get this to work. All right. So let's make that bigger and play. So this is the little dog robot, and you can sort of feel its pain as it's tasked to climb over and over again over this bed of rocks. But it's actually doing quite a good job. And the optimization problem here is that you have to design a trajectory, which is like a set of foot placements, and it's supposed to sit down at the end of it, right? That's how you know it's done. It looks surprisingly like a real Chihuahua or something, right? So, and so you have to design the foot placements and also the sequence of joint angles that let you get there, and also you have to design how you react to any problems that occur during execution. Again, I think it was supposed to do that. I think all you had to do was get your nose past a certain point. Right? This is a big DARPA program to get these. There were competitions with this hardware a few years ago. So I think maybe that's a good place to call it a day. Hopefully you guys are all motivated that optimization is a cool thing and excited about all the cool stuff we're going to learn in the course. So I'll see you guys all on Thursday.